First of all, the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. With that over, uh, welcome everybody to our first meeting of the year, 2025. And I hope the ham radio stuff goes well for everybody. Um, Tonight, we have on the agenda, uh, we have Peter. He's going to present the phase lock loop going from the theoretical to the practical. And then Michael will provide an update on the Backplane Radio and probe projects. And then, time permitting, which we probably will have, we can have open discussion or what's on the bench. So if everybody's ready to go, Peter, you can take it away.
So are you suggesting that nobody's going to ask me any questions at the end of my presentation? So that
we'll probably.
Oh, okay.
Oh, first of all, everybody please mute. I got some background noise right now.
Can everybody see that?
Yeah.
Okay, phase lock loop, going from the theoretical to the practical. Okay, so why am I doing a presentation about a phase lock loop? Well, it started off with our good friend Hassan. I had a phone call from him one morning, and he said, in response to a posting I had, he says, no, I've got a really great idea for a presentation that I'm going to do. He says, I'm in the car driving to work, and I'm going to tell you all about it. And of course, as we know in Toronto, you got lots of time to talk and to get into work. So away he went, and he's telling me, I've long since forgotten what that presentation is, and he hasn't reminded me yet either. But anyway, so as he's going along, and after about 10 minutes of Hassan chatting away about this presentation, he all of a sudden says, and you know about phase lock loops, right? And I just said, yeah, I do. And then he carried on for another 10 minutes until he got to work. So after we ended the conversation, I thought about it. And I thought, well, I understand the term phase lock loops, but I understand probably what it does at the end of the day. But really, I did not understand what it was all about or how it did it, that kind of thing. Ward Silver wrote an article on the phase lock loops in his series of hands-on radio. And I borrowed from that pretty heavy for the circuitry and stuff like that. And DigiKey Dave here in Kingston, because the Ward's article is a bit old, and I wanted to use his circuit, I didn't have the chip, and the chip wasn't available. But our friend Dave happens to have a pretty good supply of all these kinds of parts, old parts and stuff like that. And he had a couple, and he said I was welcome to one of them. So that worked out really well. So that's how this got started. So what is it? It's a PLL circuit. It is a type of a feedback control system, and it's used to synchronize the output signal with a reference signal or the input signal. And in simple terms, in step one, it listens, compares. The circuit compares the incoming signal to its own output, and then checking for differences in the phase. And then the second step is based on those comparisons. It'll make corrections to the output signal by adjusting its internal oscillator. And then once the output matches the reference, it'll stay in a line, and the circuit continually monitors it. And it's used for demodulations of signals in FM, AM, phase modulation, etc. PLLs are used to generate a wide range of frequency, simple reference clock, signal processing. PLL can be used to multiply or divide an input frequency. Example there would be RF systems used to generate local oscillator signals. Frequency tracking. It'll track changes in frequencies of a system and adjust its output accordingly. They're also found in oscilloscopes and spectrum analyzers, and they are used for precise time-based generation and signal synchronization, and it ensures accurate measurement of signal properties. Let me hide this here. And signal generators. It generates stable, tunable frequencies for testing, calibration, et cetera. So here's a block diagram of a PLL, very simple. The very first thing, you have a signal input coming into the phase comparator, which is a specialized kind of mixer, really. We all know about mixers. And then the output of the phase comparator goes through a loop filter, and then that controls the VCO. And then you can see the feedback system representing the constant monitoring of the output and making adjustments. And we'll come to the little more detail with the individual blocks in a minute. So the phase detector compares the phase of the input, or the reference signal, with the phase of the output signal. It produces an output that's proportional to the phase difference between these two signals. And the phase detector is a multiplier, so it produces two frequency components at its output, the sum and the difference, just like I just mentioned a minute ago about the phase comparator is really a mixer. So the low pass filter is used to remove the high frequency components, leaving only the desired control signal, which is the -1. And we'll talk about that in a minute. The VCO generates a signal whose frequency is controlled by the output of the low pass filter. And the VCO's output frequency is adjusted to match the frequency of the reference signal or the input signal. And then you got a feedback loop that takes the output back into the phase detector, and that allows it to continuously monitor, adjust, and correct the frequency of the VCO in order to stay in sync. Okay, so there's a few reasons why they don't use the higher frequency components in the PLL. For several reasons. Noise reduction is one. The high frequency components often contain noise, and that would lead to instability and undesirable behavior of the PLL. And by filtering them out, we ensure that only that the low frequency air signal influences the system. And the PLLs need stability. So the high frequency components, if the high frequency components were allowed to influence the VCO, it could lead to rapid oscillations or instability in the output. And then that would cause the system to lose its lock. Then there's slew rate limiting. Desired elements of the VCO should happen at a controlled rate to ensure smooth operation. And the high frequency variations would cause abrupt changes, and that would lead to problems such as a phase jitter. Number 4, I got control dynamics. The PLL is designed to track changes to the reference signal gradually, and that's why you don't want those fast, high-speed changes in it. And that would cause, because that would cause the VCO to have an erratic output, and that's not very practical when you're trying to have a stable and precise frequency generation. So by filtering out the high frequency components, the loop filter ensures that the PLL responds appropriately to slow changes in the phase and frequency, maintaining synchronization effectively. Okay, so I have a little chart on the bottom right there, and then I'll talk about each one here. So there's a few modes of operation, 4 that I've listed here, and the first one is called free money mode. So when you got power applied to the chip and there is no input signal applied, the output frequency is at the design frequency. So you control that. The output signal of the VCO is in a free running mode, and that may exhibit frequency drift or stability over time. So if you look at the pictorial down there, you can see the free running frequency is described by FO, and it's right here in the dead center of the pictorial there. So capture mode, which is the orange, or the range in this area here, that's the process of the adjust and hold, and it's called the capture range. And the capture range of the PLL refers to the range of input frequencies over which the PLL can acquire and lock onto the incoming signal. So if your frequencies were out in the yellow area, and you're in free running mode, and your PLL would not lock onto those frequencies outside the capture range. Lock mode is when the input signal equals the output signal, and the lock range of the PLL is in the range of the input frequencies over which the PLL can maintain synchronization with the incoming signal once it has acquired it. So to acquire it is a much shorter range than what it can hold on to, if that makes sense. And the pull-in range refers to the frequency range around the nominal center frequency in which the PLL can adjust and lock onto an input signal. So if you have a signal that's out here and it's coming down into this area here, the PLL will not lock onto that signal until you come to this part here, this section here, or coming back down in this way here. But once it's locked in, the signal can drift up this way or down this way, and the PLL will still hold on to it until it gets to the end, and then it loses it. Hope that makes sense. The old days, you can get it in the dual line package, or you can even get it in a metal can, or at least you could at one time. Nothing really to go over it here. It's just to show you that on the data sheet has some pretty good graphs in here that you can see where the the functions of the lock-in ranges versus the input voltage, all that kind of good stuff. But we don't need to go into this detail here. So here's the schematic of what I did for the test setup. I did do this to take into account with a 5/5 timer. I was going to also do some demodulation experiments, and I really didn't do that. I did see where it was doing it, but I didn't pursue it enough to put it into a presentation. So this is what some of this other stuff here is for. But anyway, so here's our LM565 is what I am using. The components here in the green is what you use to adjust your free running frequency. So your combination of this capacitor and these resistors. So in a real world, you would just use a capacitor and one resistor. I use a pot in here just so you can play with it and see, get different free running frequencies to play around with. So for the capture range adjust, what I did was I set up a pin header, and I put in 4 different values of capacitors. And what I did to select them is I just had a jumper wire here, and I just jumpered out to whichever one I wanted to bring into the circuit. So this here comes over into the terminal that's called VCO control voltage. And that's pretty much it for this slide. There's the test board that I milled and populated. As you can see, I was a little bit careless with a soldering iron. And this was for the 5/5 timer. I may come back to it one day. We'll see. And then over here is the pin header for the capacitor adjust. So here you can see some of the larger capacitors, and then the smaller value ones are tucked in down underneath here. And then a couple of test points were in here. So I guess I won't go through all these numbers because you'll probably fall asleep. But really what I did was, because I had 4 different values and 4 different tests and stuff, the first thing I did was I just wrote down, it was getting a little bit confusing when I first started. So I just wrote out each task, what I had to do, and then just ran through each step with the various frequencies of interest, shall we say. But the long and short of it is, as these capacitors here, which is tied to this control here, as they go down in value, you can see where the range is increasing. This is in kilohertz, by the way. And they're not really, I don't think they're linear to each other, but anyway, this gives you an idea. So the whole thing that comes out of this is that as you decrease your capacitance, then it's you're getting an increase in range. Now, I didn't try anything to go to the extremes, but that might have been an interesting thing to try to see if it did flatten out. And I think there's actually one in here starts to show where it's flattening out here on the free running frequency. You can see that. Oh, sorry, no, not the free running. That doesn't change. Yeah, this one here I think is the one. Anyway, we'll forget that. So here I got a. I set up just to do a little video of the going through the upper and lower of the frequency, and then watching it capture and then lose the signal. It'll snap right in. Now we're locked, and you can see as I'm increasing the frequency, it's still hanging on to it's still following it. And there we've lost it. So in summary, PLL locks the phase and frequency of its output signal to the reference signal or the input signal, and that by using the feedback control. And by continuously comparing and adjusting, it ensures a stable synchronization, making it a crucial component in many electronic systems. So if anybody is now encouraged to go out and try one themselves, there's some cheap and there's some expensive chips out there to play with. The first one up there is the CD 4046. That's kind of I probably even have one of those sitting in my bin somewhere, and probably everybody else does too, maybe. Anyway, if you don't, that's 71 cents of an afternoon's worth of entertainment. The next one is, well, that's a little bit pricey. I don't care how good it is, at $33. And then there's another one. This one we're all familiar with here, the SI 5351. That's $526. So, but you know what? Maybe some of us have those in there because at one time we were buying them for a lot less than that. And then there's the CD74 HCT series of chips. So there's some nice chips out there you can play with. Okay, and that's it. I heard somebody asking questions. You'll follow up on that one, Ken?
It's Michael. I have a question. In the 14th graph, the one with the sine wave in it, what is the square wave on the top?
The sine wave?
It was number 14.
No, number 14. Oh, there.
Yeah. So yeah. Okay. The I could see the frequency moving, but what's the square wave stuff at the top?
This is the output of the PLL.
Oh, okay. And it gets fed back in and locks the frequency.
Yeah, and then this is the frequency that you're adjusting to, and then it'll lock into it.
Okay. Thanks. That's good.
Go ahead, Dave.
Yeah, Peter, that is a really cool video. I love that video where you see it locking in.
Yeah, it's kind of neat.
Locking and then you're losing it. That is a really cool video. I love that. That's nice. Anyway, I just had a comment. Nothing about this. The SI 5351. Yes, it used PLL, but it's not a PLL. It's a clock generator, right? That happens to use a PLL. But it's not a PLL. So if you're going to want to experiment with PLLs, you don't use SI 5351. If you want to play around with a clock generator, if you want to generate signals that uses a PLL, sure, use the SI 5351. So it's just a matter of, that's it, Peter.
Yeah, and it was interesting too, because all I did was just copy it out of a document. And what I found, another thing interesting too, when I talked about the 5351, one on the applications, it says ham radio. Well, hey, we got some popularity there. But yeah.
Eric, go ahead.
Peter, that was interesting. I'm just curious, though, in your video again on slide 14, if you were to reduce the frequency, would it unlock? Like you didn't.
Either way,
but did you try that?
Once your PLL is tracking or it's locked in, if increasing your frequency. Here, let me go to the. Okay, so let's assume that your frequency wandered into the orange area.
Yep.
Now your PLL will lock onto that. Now your frequency can wander past the capture range into the hold range, and it will still hang on to that frequency and lock onto it until it goes above it. Same thing with going down. Now, but again, it can hold on to a frequency better than it can capture it. To capture it is the bandwidth isn't quite as wide as the hold range, if that makes sense to you, Eric.
Right. Okay. But did you try going outside of the lock range at all in your experiment?
Right over here. You see over here in this data here?
Right.
You can see like under the here for the 10 megahertz or 10 microfarad capacitor, the lower capture range here was at 18.88 kilohertz.
Oh, now, so these were measured by you. Yeah.
Yes. And then the upper range was at 19.6.
Yeah.
Up here, here. Capture range is here, and then your lower lock frequency and upper lock frequency. This is where it loses it. So once it's locked in this particular case, it loses it at 13.5 and at 25.1. Now switching to the smaller capacitors, you got a larger range of being able to hold on to it.
Right. Yeah. Okay. Cool. Thank you.
Go ahead, Hassan.
Yeah, Peter, can I? No, it's okay. I just wanted to see the video again first.
Sure. Yeah, I guess I could have done a little bit different, but anyway, it is what it is.
Let's see. And
so here I think I'm starting off, I'm going to be decreasing the frequency. Now it's snapped in. Now I'm increasing. And I've gone beyond where it locked in. And we've got
interesting. So I just wanted to make one point, which is PLLs kind of cheat a little. So what happens is they track the phase and the frequency of an input signal. But if your input signal varies in phase, like most PLLs have a VCO, a voltage controlled oscillator, so they change. It only is adjustable in frequency. So they don't just like adjust the phase until it locks. What they actually have to do is go boost the frequency up until the phase lock is kind of there, and then they should come down again. That's the only way they can.
No, they're not adjusting the phase. They're comparing the two phase. They're comparing the phase of the VCO output and the input signal, then it's outputting a voltage out of the comparator based on that phase difference. So as the phase difference gets closer to closer, the voltage output is, I'll just guess, I've got a 50-50 chance of getting it right, is less, right?
Mm-hmm.
And so the does that make sense to you, Hassan?
No, it does. So what happens? Let's say your input signal is a sine wave, and suddenly let's say you got it. It's locked in.
Yes.
Now you suddenly change the phase of your input signal by
not the phase. No, not the phase of the signal. You're changing the frequency of the signal because the comparator is comparing the phase difference between the input signal and the VCO output.
No, I get it. But the thing is, I get it. The phase comparator is telling you the phase difference. But let's say your input reference signal changes in phase by 90 degrees.
Okay.
So how does the PLL reacquire a lock? It detects the phase difference. The output will go really big or small or whatever, one direction, after the loop filter. And then the local frequency is going to shoot up or shoot down. And then it's going to oscillate, like overshoot and then come back down again until it's reacquired the phase lock.
I'm not sure I can experiment that, but what would cause a signal to change a phase like that? That would have
maybe it's PSK, phase shift key.
Oh, I see what you're saying.
Yeah, or it could be you're driving and it's something like that. So PLLs, when they respond to phase changes, they do it by the frequency has to swerve up and down, and it does that. It swerves around until it reacquires a lock. So that's the cheating part of PLLs. Like they're always hunting for the phase, but they do it by adjusting their local oscillator frequency.
So you're saying if I change the phase of the incoming signal.
Yep. Yeah, you'll see the frequency do a really oscillatory thing until it reacquires the lock. And that'll be, okay, it's an imperfect process.
So let me question you a different way then. If it's a small phase adjusting that's going on, the PLL will just ignore it. Well, no, it could adjust it. It'll adjust the frequency accordingly, even though the frequency of the signal has not changed, other than the phasing going back and forth.
Yes, the frequency will hunt around. You'll probably need like a dead times, or it'll be like a noise level, but that's what the whole design thing is. You have to tune everything just right so that it behaves properly.
Does our SIG-Gens output a phase shift signal? All right, you're making me think again here on this project. Well, thanks a lot, Hassan.
Yeah, that'll be a fun time.
Okay, I'd like to test that somehow.
Yeah, just flip it.
Yeah. So, or you could use a function generator and have a phase control knob.
Yeah, you know what? With these SIGGENs, you can design your own signal that you want to put in the thing, and it'll output it. Okay, all right. There's food for thought. Okay, well, thanks again for another presentation. You're talking me into, Hassan.
All right, no problem.
Okay, I think Michael's next.
Just a quick question relating to the slide number 12, which is where that hold frequency. What's the difference between the hold range and the capture range? What's the difference? Like, what is it?
Okay, so let's say if the frequency is where my cursor is.
Yeah.
As it's coming into here, it's now come into the hold range, but the PLL will not lock onto it. The PLL will not lock onto that frequency until it drifts into the capture range.
Okay.
Once it's in the capture range, the frequency can now drift back down here, and still the phase lock loop will stay locked onto the signal.
So once it's caught, once it's captured.
Yes, the capture range is much narrower than it is much narrower than the hold range. So in other words, once it's got the signal, it can hold on to it longer.
Mm-hmm. Okay, thanks. That's fine.
All right, I think Dave.
Yeah, I think Michael. What I got a couple of comments. One, Michael, I think that hold range is a buffer from what Peter is saying. That's just a buffer to say once it's locked, it allows the signal to drift a little bit, and I'll still keep it locked until it drifts outside the hold range. Then it loses it. Okay, and the phase thing, Peter, I think makes sense. From what Hassan is saying, I got to remember my question I was going to ask you because I'm talking about other things. Because other questions came up, and I wanted to comment. So so that's very interesting. That if you change the phase, because that'll impact my next question I'm going to ask. Because what Hassan's saying is that if you've got a signal coming in and it's locked on, is the signal's working, and all of a sudden there's a little bit of a phase shift because of maybe the atmosphere, or you're bouncing off a wall, or you got an extra path or something like that. In the case of RF, then you could lose a lot. Like the way you could generate that phase, you could do it with the SIGGEN, because the SIGGEN has INQ.
Okay.
So one output is 90 degrees out of phase with the other output. So you just got to feed the other output in, get some kind of a switch, and be able to feed clock 0 or clock 1, and they're both 90 degrees out of phase. So you could do something like that.
Okay, I have to think about that.
But anyway, my question, Peter, as you were talking about this, as usual, in the back of my mind, it's cooking. It's looking at, hey, what can we do with this? And it seems to me, could we not use this somehow to detect CW, so it'll lock on to a CW signal? If you've got like an audio tone coming in, right, to say your PLL now is working on the audio stage of your radio, and you got this audio tone coming in, and you lock on to that audio tone. So if it's there, the PLL will lock on, and then you could get a signal saying, yep, dit or a da, and look at how long it locks on for, and that's the duration of your dit or da. So in theory, I'm thinking, could we not do something like that with it?
You might. I just don't know how. Like when I was saying earlier on, the PLL doesn't like fast shifting things, right?
Well, no, but it's an audio frequency. It's like 700.
So we should go in there. I don't know, Dave. I mean, it's.
So I don't know. It's just a thought. It's just, as I said, I sit here and I look at this stuff and I go, "Oh, how can we use this?"
I'm thinking now, as you're talking there, maybe a Schmidt trigger might even do the same thing a little bit better, a little more cleaner. But well, maybe.
No, a Schmidt trigger looks at a voltage level, not a frequency. It looks at a voltage level.
Right.
So it says that, okay, once your voltage is above 3 volts, lock it.
Well, that's what I'm getting at. But yeah,
No,
I suppose anything's possible.
But you're not looking at voltage level. You're trying to lock in on a frequency. That way, if you've got one CW signal at 700 hertz, another one at 1200 hertz, another one at 1400 hertz, you could pick which one you want to lock in on.
Okay. Now I see what you're saying. That's an interesting thought. And you just have to take a look at your range, because you can see here's the capture range here. You know, if you use the 10 microfarad capacitor, you're at 0.8, right? Now, I don't know. I never tried what the 20 would be, or a 30 microfarad capacitor, for example, but you can narrow down down to a more appropriate capture range that you would be wanting to do, right?
Yeah, just say something I thought about, and I thought I'd throw it out there.
That'd be another interesting experiment to mess around with and try and see how that works out. Put it on the list. Just before we move on, I think it was Michael that was asking about the difference in these areas. So here's the numbers. So the lower capture range, when in the 10 microfarad capacitors is in use, is at 18.88 kilohertz. But so as the frequency is coming in, it won't lock on until it hits that 18.88. And once it's locked on to that frequency, that input frequency can now drift down to 13.58 before it loses it. So I don't know if that makes a little bit more sense, Michael, or not, but for what it's worth.
Okay, fair enough. I need to think about this. Thanks.
Okay.
Go ahead, Hassan.
Yeah, about Dave's comment, I've never heard of an audio frequency PLL, because I think at audio frequencies you can just do an FFT and that gets you the same results, and it's a bit cleaner, like it's a bit more precise. So I think PLL might be overkill or underkill for this application.
So
hey, why make something simple, Hassan? We could complicate the crap out of it. Like, come on. Like,
so really, one question here then, Hassan, would be the highest capacitor value I used was 10 microfarads. I'm sure there's a limit, because as it goes up higher, things are slowing down. But I mean, can I go 20, 30, 40, 50 microfarads?
Well, the way to think about it is, your capacitor is a low pass filter. So as your RC combination, you just make the filter cutoff frequency, and that essentially it tells you how fast your signal can change. So a slow,
That's right.
low pass, yeah. So like a really tight low, what's the right terminology? Like a low pass filter if your low pass filter is really low frequency, you'll lock pretty well, you'll hold it. But if the signal moves too fast, like if the frequency or phase of the input signal changes too fast, you lose the ability to track it.
That rings the bell, because I do remember reading about that. As you got to keep in mind the capacitors the larger the capacitor, the slower things are going to be. It could miss things, is what you're saying.
Right, it won't be able to track fast changes. It's like a really slow. But the thing is, if your low pass filter has a high frequency, you can track high frequency changes in the input, like like a audio frequency or something. But then it's also subject to noise. So if you have a steady signal, the PLL will be hunting all the time, up and down, up and down. It won't be. It'll never be fully locked on. So it's all trade-offs there.
Yeah. Okay.
Anybody else? Okay. I got a comment too. Like you, Peter, I knew of them and just a general how they work, but not anything specific.
Mm-hmm.
And the first thing I thought of, why are you comparing two phases? And then I just realized that you're feeding the signal back to the comparator to produce the offset that needs to be adjusted.
That's right. The two phases are compared here, and then the comparator outputs a signal based on the differences of those phases. So as the phase changes, as the phase differences change, this voltage changes. And because it's a mixer, you got the plus and the addition and the subtraction signal. So you got two signals coming out of here. This gets rid of the high stuff and then inputs it into the VCO. So, you're inputting this voltage into the control VCO, and then where your adjustment goes, right?
Yeah, you had a slide. You had a slide there with the pinouts.
This one or this one?
Uh,
Well, this one, there's your pinouts there. What were you looking for in particular?
the one before. Yeah,
So
so you got two inputs. So I'm assuming that the VCO input is. Hang on a second here.
Well, you put your phase lock loop. So you got input 2 and 3 here. Let's see what I did in the schematic. So here's 2 coming in. Where are we here? Well, one will be your reference voltage, and the other one's going to be your
Ground.
your return, right? Or the feedback loop.
Isn't that a differential input?
Don't know. I did not break down the chip into that degree. That might have been an interesting thing to do, but I didn't do that. In one, I called it in one. Where are we here? And then 2. No, that's something different. I'd have to go back to it and just double check on this one. So 2 is a little bit different than what I thought. So here's your VCO out, and then going back into VCO in. Okay, there's your feedback. Yeah, so there's your feedback, and there's your incoming signal.
So it does have two inputs.
Yeah, but in this particular case, you're grounding. And to be honest with you, I've forgotten now what the reason for R5 is in this case here. There is a reason for it, but I forgot what it was.
Probably to tie it down to ground so it doesn't cause any noise.
I can't remember. I'd have to break out the sheets, and of course, I don't have the. I should have actually had the sheets in front of me for the presentation, but I forgot about that part.
Okay.
You can fire me if you want.
Nah.
Okay.
It's okay. Are you happy that there was lots of questions?
I have sort of a basic question, Peter.
Mm-hmm.
The capture range adjust. So depending on which capacitor is grounded, which capacitor is connected, that does something to the control signal.
Yes, and it directly influences these ranges right here.
Okay, I can't see it just looking at the circuit, but yeah. Okay.
It influences it to the degree of what you're seeing here. So just you just pick one. If you just want to say, okay, the lower capture frequency is 8.88 with a 10 microfarad capacitor. But if you're using a 1 nanofarad capacitor, the lower capture frequency is increased up to 11.68 kilohertz.
Mm-hmm.
So that's how those capacitors influence those range values, and it does the same thing accordingly to here. If you go to the upper capture range, as the capacitance is changing, your frequency range is increasing.
Mm-hmm.
So it's like a little window moving up, if you will.
Okay.
And again, the same thing with with your lower lock, and your upper lock, they all follow down that way. So really, in effect, of your capture range, so the total range, so from here to here in the orange, come over here with a 10 microfarad capacitor, that thing's only 0.8 kilohertz wide. If you put in a 1 nanofarad capacitor in there, that capture range is now increased to 14.9 kilohertz. So it depends on what you want. And that's what's going to determine what capacitor value you want. Does that make sense?
I think so. Okay. Yep.
Okay. Anybody else have questions or comments for Peter? Oh, good. Thanks, Peter.
Okay, good.
That sort of opened up things for me anyways.
Good.
Guess I got some reading to do this weekend.
Well, You know what? Reading's great, but put it on the bench.
Yeah. Yeah. I got to make some room for it, though.
Only one chip.
Alrighty. Great. Michael, you're up next.
Okay. This is just a status report, really, on what there's a couple of teams been set up to. Were set up in early December to look at. One project was to design a probe that you could put into a circuit that would measure a circuit characteristic without affecting the circuit itself, but for testing circuits. And the other team had to do with a backplane, setting up a backplane radio device. So to start with the probe, there's a team. The team consisted of Dave, Peter, myself, Hassan, and Eric. And the idea was to be able to develop a probe that would be able to test a circuit without influencing the circuit behavior. And so we needed a circuit that had a high impedance input, so that it didn't affect the circuit under test. So the intent was to take a low level signal, and amplify it so that you could look at that signal on a spectrum analyzer or on an oscilloscope. So we've had 5 meetings so far, from early January and December to now, and at this stage, Dave and Peter have been working on various designs. The preferred circuit has a MOSFET front end and a basic BJT transistor as the output amplifier. And Dave now has a proof of concept board that's working. So that's where we are with that. Just looking to see my notes here. It's very promising because Dave had actually thought to use 2 different circuits in case the one didn't work out. Looks like the preferred one with the MOSFET is working out. So what we're doing at this stage is Peter and Dave are completing the testing of the proof of concept board. And then what we're going to do is we're going to distribute some of these boards out. You can get 5 from five boards from JLPCB. So we're going to distribute some of those out and try populating them and see if we can test them ourselves. The intent is to do finalize design sometime in February. The idea being that in March, perhaps, we can do a buildathon based on this probe. And also at Field Day in May, the intent is to take a presumably working prototype to FDIM. So that's the first one. The second team has to do with, and that team consists of Peter, myself, Hassan, and Charlie Gale, and Wayne Harrison. And the intent is and there's been 2 meetings so far since early December or late December. And the intent is to design a radio or something like that with using a backplane that basically, and the JL PCB boards are 100 by 100 millimeters. So we'd use one of those. And that's the sort of, the backplane provides the signal traces and whatnot. And then you plug into that backplane a board, for example, a filter board or a mixer board or a audio amplifier board or whatever it happens to be. And so you'd plug in, ultimately you could do something like a software-defined radio. All the pieces for an SDR could be plugged into this board in one way or another, signal will be introduced using some kind of coaxial cable to the boards, and the backplane itself provides all the DC and the control signals and whatever. And there'd be a basic power supply that's plugged into the backplane that would provide power at whatever voltage for all the other circuitry. So yeah, so what's happening now? There's been progress in laying out the backplane. Charlie did a lot of that, all of it actually, and figuring out what signals are going to be on the backplane, and it's a longer term project. Going to go for a little bit longer, quite a bit longer, I guess, and that's where we are. And the suggestions have been made that individual team members might take on a particular plug-in board, like an amplifier or like a audio amplifier or like a filter that would be part of another radio. Anyway, so that's where we are with those two projects. Been interesting. I'm the scribe, so that means I have to sort of know vaguely what's going on. And yeah, and we've got a couple of Google Drive things set up so we can keep notes of meetings and results and everything else in one place so everybody can look at. So that's all I really had to say. No comments. That's good.
I had to take off for a couple minutes here. Did you talk about the probe as well?
Yes, we did. That's how I started. Yes, I did.
Okay, I'll watch the recording.
Okay. Or I can talk to you later on if you want. Whatever.
Well, basically, you could say about the probe, really what it is, there's been one prototype's been built. I'll be building the prototype as soon as it shows up in the mail. And then I'm going to validate Dave's findings.
Mm-hmm.
And once I validate Dave's findings, if I agree with what his findings are, then we will fine tune and move forward. If I find there's a big discrepancy, the better, that's yay. If I find the discrepancy for the worse, that's not so good, but it's still not good either way. But anyway, that's just to oversimplify. It's just that I still have to build my board because I haven't got the boards yet. And once I do that, then we have to build it, and then I got to validate Dave's findings. Then we'll go from there.
Okay, cool.
Yeah.
Cool. Alrighty. No other comments or questions? Very good. So let's see. Since we've got the agenda done, does anybody want to bring something up? Any discussion or any questions? Go ahead, Pete.
Whoop. Where are we? Okay. I thought Howard posed an interesting question for the DCR the other day. It was one that I never considered with the latest version of the DCR and the earlier versions of the DCR. And when I was doing some testing on the bench, it never occurred to me at all. Does it make a difference if you change the duration of, or does it changing the duration of the square wave? Does that affect the performance of the DCR?
Well, as I commented in the thread as well, I've never looked into that. I've never tried it. It'd be interesting to see what happens.
You know, because right now I think it was, 50-50?
Yeah, something like that.
Yeah, I'm wondering if, like what happens if you went, actually, it probably wouldn't make any difference now I'm thinking of it.
Well,
until you try.
It might when you get really low.
Yeah.
That'd
Yeah, like a very short pulse high and then a very long drawn out no voltage. Yeah, that probably would do something. Yeah.
Yeah.
Anyway.
I remember. I'll try it out this weekend.
Marty, you had your hand up.
Yeah, is my sound on? Yes, it is.
Yes, it is.
Does anybody have a Q4 working?
No.
Well, I have a Q4. it's been a few years since I've had it running, and actually I don't even know if I could get it running because I don't know if I even have that printer cable that we used to plug in it to control it, right? Oh no, it's not a printer cable.
And what's the Q for?
It's a software-defined receiver.
Oh, okay. Yeah. Okay.
With multi-band.
It's been a long time.
Multi-band.
Yeah, I can't remember. I can't remember the last time I turned it on. Why do you ask?
Because I've got one that's not working.
Oh,
And I think it would work, but I think it required a software disk or something, a driver or something.
oh, okay. Then while we're chatting, I just happen to have right here Q4
Right.
docs, but I
Well,
wouldn't. Oh, I don't have my laptop here, so I can't open it up.
Don't do it now, but for another meeting.
Yeah, I don't think. I'm just going to do a quick look over at the old Park Homebrew site and see if it was uploaded. If not, maybe Frank might have the driver.
Yeah.
If not, I'll take another little look and just see.
It's too bad to have the thing sitting on a shelf, not operating. That's all.
Did you? So we had to have a driver for it, did we? Because I thought it just ran off of. Oh, yeah, but the driver came from the software that we used to control it, didn't it?
Yeah.
Oh, is that the one that uses the soft rock?
Yes.
Oh, okay.
No, there's nothing on the on that group. Okay.
Isn't it using Rocky for the software?
You can use Rocky, or you can. No, we were using. What was it called?
SDR Sharp.
No, it wasn't that one. It was WinRAR. We were
WinRAR.
using WinRAR, and you downloaded the DLL file from. I can't remember where now. If you Google WinRAR, I forget the guy's name and call sign, but Alberto, I think his name was. The website is still active, and the Rocky stuff. Those websites are still there.
You could also check with the soft rock group because somebody took over from Tony.
Yeah, but the really good documentation is done by another guy, American Hand WB5 or something like that. But if you Google it, you'll find reference to it and go to his website. All the construction documentation's there. But I think what you need to do is go to while we're chatting, I'll take a look. WinRAR. It's starting to come back to me now. I think when you use WinRAR and you install it, it's gonna. Oh, that's not the place. You have to download a DLL file, I think it is, and then that's what will end up controlling the Q4.
Yeah, and I think if you go to the soft rock group, the that guy you're talking about has build notes there, has links how to set it up and everything to go.
Yeah.
Oh, cool. All right. Yeah, because I know. Well, if you're using a soft rock, you can use Rocky. You can use HDSDR, WinRAR. Like there's about a half a dozen of them that you can.
Yeah, I think the one that we started to use was WinRAR. Anyway, I'm going to put in the chat the link to the build documents. But I don't think the build documents are going to give you I could be wrong, but I'm not sure they talk about the software, what software to use with it. So you're better off to just Google WinRAR, find it that way. And maybe you know what, whoever built these stuff, maybe even ask Frank. I might even have a disk somewhere too that will have WinRAR on it, or those kinds of things. I just have to look.
Thank you.
All right, no problem. Anybody else have something they want to discuss? I guess not. Well, the last meeting that I was at, I was talking about that kit from Rex. What a mess.
Which kit was that?
What's that?
Which kit was that?
That was the WWV receiver. It was like our, much like our DCR, except he's got plug-in boards for different frequencies, and he uses crystal. And I don't know if you remember, but the build instructions are for kindergarten.
Well, you got the Canadian rep right there. You can complain to.
Yeah, never mind. So I actually got it figured out. Had it a lot of circuit tracing to see where pins are going and traces are going, and everything. And his, for example, is using a MV, think it was MV209 Varactor, and he had a little screenshot in the build notes where the front of it was facing the back, but he had a note on there with an arrow saying it should say face the front. And very, very difficult.
Honestly, though, you should mention it to him. I mean, he's actually got he sounds kind of reinvigorated. He's got some things in the pipeline that he's working on for 2025 that are a bit of a departure from what he's been doing. So, but I'm sure he would respond favorably to any constructive criticism. So, if you want to fire me a message briefly with your beefs on it, I'd be happy to bring it up with him. So.
No, I could send him something. I'm just trying to. It's working, but it's not pulling the crystal in the right direction. So I got to figure out why.
Yeah. I mean, there's errata that he hasn't, maybe he said, oh yeah, when we were doing that back in the day, I sent out, the updates or whatever, and I forgot to update the original whatever. So I'm sure it's something like that, knowing Rex. So
yeah,
bit of a scatterbrain, but good heart.
Yeah, well, all the documentation's from 2019, and I think the problem is that he was doing a buildathon at that time with it, and he at the last second he was putting together build notes, and as it turns out that the build notes didn't work the way he wanted to, so he had to do some fancy footwork to get it going at the buildathon.
Probably because he was writing them at 3 a.m. the day of the buildathon. So
yeah, probably. Yeah. But once I get this pulling of the crystal, then I'll put something together.
Yeah.
It's kind of like it doesn't really bother me. The part that bothers me about it is he's charging $50 US.
Yep.
Translate the Canadian bucks, plus shipping. Like that's a pretty expensive DCR.
Right. Yeah, no, absolutely.
Yeah.
Yeah, I think I might even have the WWV receiver kit. I haven't assembled it, of course, like most of my kits, but yeah. I'd be interested to find out what your comments on it are. So
yeah, well, maybe what I'll do is I'll make an offer to him. You send me blank boards, I'll write you a manual.
Right.
And then recoup my cost on the kit. But go ahead, Pete.
Okay, I put in the chat the WinRAD software for download.
All right, cool. Go ahead, Marty. No?
I said thank you.
Oh, okay. Thought you put your hand up. So, what do you guys want to do now? You want to do on the bench? Sure. Okay. Well, I've already gone through mine, so I see Marty next in line on my screen. Or sorry, Al.
I don't really have a lot to report. I don't have a bench right now. It didn't survive the flood, so I'm a shackless and workshopless ham radio guy.
You could do it in your bed.
What's that?
You could do it in your bed. Sorry, Eric, you're next in line on my screen.
Oh, okay. I'm still unmuted too as well. Yeah, just working on the enclosures for the active probe. I've got it in my mind to order a few boards of various sizes from JLC PCB to approximately what we're looking at for the final product for the active probe, and work on making enclosures that'll work with it for the final product. So that's really my the front and center with this going on. So that's about it. I mean, I got a pico ballooning project going on with another group, electronics meetup group in Toronto, that is tangentially related to this group, I guess. But that is, so I actually invited a guy to come here tonight. His name is Eli. He heads up that group, and he sounded interested. So he did not make it, obviously. So hopefully he'll show up at a future meeting. But he's interested in not only the pico ballooning, but also getting his license. And he is a tinkerer as well. So we'll see if he shows up. But anyway, that's about it.
Very good, very good. Hassan, what do you got going?
Current project is my sim rig. So it qualifies as a bench of some kind. So just lights, LED lights related to that, and stuff like that. And everything else I'm doing is 3D printer related. So getting back into Arduinos and microcontrollers. I've been pulling them out and using them again. And I'm going to confess, my weak spot is soldering and packaging these things. So I have to get away from using jumper wires and breadboards and up my game on that front. So that's what I'm currently thinking about. And I'll get back to radio. Actually, yeah, back to radio soon.
Yeah, very good. Howard, what you up to?
I haven't been doing too much. I put together the DCR receiver. Oh, that was fun. And maybe down the road do something with it as a platform to work on other things. So that's pretty well it.
Cool. So your DCR got up first time?
Yeah, once well, not the first time. It was finger trouble with the signal generator. So technically, it probably would have worked the first time if I had the right frequency set, but I didn't.
Yeah. It's all right. It's all right.
So it worked the second time.
Another successful story. Michael, what you up to?
Not a lot, actually. But I did, out of interest, a few things. I took the SS4X4, the little signal source thing, and I took mine and Daniel B3NI's and connected up to the spectrum analyzer, and just to see what it would show, and it showed the signal levels about what I would expect. I ended up expecting, more or less. I took things too literally, I think, and I figured, well, minus 70 dBm, it should be exactly that, but it's not. So fiddling around with that. I'm going to be. The plan is for me to take Dave's printed board for the probe and have a look at it with my oscilloscope and my spectrum analyzer and the signal generator, just to verify and learn how to do this stuff properly with my own equipment, which would be interesting. The other thing I've been fiddling, I just started tonight. I have I've got some network cables from Daniel, and I'm going to connect my spectrum analyzer and my scope and my signal generator to my network and see if I can make it work. And I got as far as plugging one of the cables in, and that's as far as I got. And the other thing is I bought a backup program for backing up stuff onto in my case, I've got the three. We have three computers here all together, Margot and me, and I've got passport drives sitting backing, and I'm backing stuff up onto the passport drives. It happens every time the way it's set up when you shut the computer down, or there's a schedule and it backs it up, and it sort of works. It seems to work okay. So that's really what I've been up to. I haven't done anything with the DCRs. I've got two DCR kits. Daniel's got one, Wayne's got one, and at some point we're going to have a massive buildathon at my place and see if we can make them work. Anyway, so not really very much, but that's about it for me.
Well, it's more than I've been doing. Lucky you. Peter, go ahead.
Just saying. See, Kingston was the first to build the DCR. Just saying. Right, Howard? Okay. Marty, I put another link in for the DCR for some that WinRAD. I think it has a lot more detail there for the WinRAD software. That's what we were all using originally. And when we were chatting, I went and I decided just to take a look through my bin here. So I got a SDR software, Q4 Part 1 disk, another one Park, another one Q4. So I got a bunch of CDs with some files on that probably be pretty good. I only got one computer with a CD-ROM. You know, it just occurred to me, not many computers left with a CD-ROMs, and I got all these CD-ROMs. Anyway, CD disc. Anyway, whatever. Now you got me a little bit curious too, as Hassan got me on PLLs. Now, Marty, you might get me thinking about the Revive the Q4 project, because that was a really, really fun project, and I learned a lot about SDR stuff in there that's all forgotten. And now I have to remind myself of it all, because the Backplane project is going to eventually involve an SDR transceiver. Anyway, I've been doing a gazillion LT Spice simulations with our Pro project. Some stuff with KiCad as well, mostly proofreading and whatnot. But it's amazing how you can get how much background work goes into these projects. And it's 2 active components in this project, and the hours are climbing. But anyway, it's been kind of fun. It's been a pretty good learning experience as well too, running all these different simulations, because you're doing transient analysis and AC analysis and all these kinds of good things. Building, I don't see anything. I don't think I've been building anything, because I've been doing so much, the background stuff on the Pro project. That's taken up an awful lot of time. The Backplane project as well, giving that a lot of thought. It's hard to keep focused on the Backplane project, because you're thinking, oh geez, what about this board, and then what about that board, but anyway. Other than that, I think that's pretty much it from my end.
Alrighty. Cherry, good evening. Go ahead.
Hey, good evening, everyone. So on my bench, I'm doing something called okay, I hope you can see this, Alt Tuner. It's from QRP kits I picked up from Dayton, from the Hamfest actually. The kits was in a kind of container, and then I'm actually doing this right now. Yeah, that's what I'm doing. It's a long wired tuner actually from QRP kits. I can post link here. I just started with some few resistors a while back, but yeah, still hoping to complete it soon. The thing I like about this is they have lots of toroids to wind, so I'm always interested in toroids, and then it goes into an Altoids box. So that's what I'm trying to do. That's all. Thank you.
Cool. Oh, screen shifted on me. We did Hassan, and then Peter. Ian, what you been up to?
Oh, it's been very busy here in the shack. So I'm continuing on with my little streetcar control system here. Trying to build my own simulator for it so I can do my card testing. So this week I need to simulate all the contactors that are under the car and their feedbacks. So found a bunch of relays that I can do that with. So the next thing I'm working on, there's like a diagnostic port on the front that gives you like feedback for all the signals. And normally it's a giant box. It's got one analog meter, and you can switch through like 20 different signals that are analog, and then it has lamps for like a digital kind of signal. But I want to bring that into something a bit more modern. It'd be kind of cool if I can have something go off the plug and then go into like an ESP32 so I can pull it up and see all the signals at once. So I'm trying to figure out how to do the ADCs. So it's a positive 15 to negative 15 analog signal. So I need to get it down to the 3.3 that the ADCs will take. So I'm trying to figure that out. So I'm lost experience in digital signals. Now I'm falling off the deep end into analog. And I'm trying to figure out how the heck. So I'm going to have to, I guess, scale to get the plus 15, minus 15 to plus and minus 1. And then use an op amp to shift it up into 0 to 2. Anyone have any? Are there better ways to do that? To get a plus and minus 15 into something an ADC will read?
What about a simple switch divider?
It's plus and minus. The ADC is 0 to 2.
Oh,
It's the minus that's throwing me off everywhere. I didn't have the darn minus, but the signals have both. So it's like I got a voltage divide, I think, to scale it down, and then use an op amp to inject 1 volt to bring everything positive. So that seems to be what the resources I've been finding say to do so far.
Summing amplifier. Yeah.
Yeah.
You need to scale it down first for the volt, or scale it down first and summing divide, or you sum it, add 15 volts, then you get 0 to 30, and then voltage divider.
Yeah. I'm thinking voltage divider to scale it down, and then summing amplifier to. Does anyone make like a integrated for that? Because I need like 20. I have 20 of these signals. It's a lot of op amps.
You can probably buy an instrumentation amplifier, but I don't think it goes 0 to 30. You put the voltage divider first, and then
that's what I'm thinking. Yeah.
Plus or minus 3, and then instrumentation amp. If you get a bipolar instrumentation amplifier, it's monolithic, and feed it with plus minus polarity supplies. And the other option is you wind it on toroids. And a balun kind of thing,
Yeah. I'm trying to get it where I could like SMD it and just have it off the connector so I can leave it in there and have it run on Wi-Fi so I can actually just have my iPad. So I want it to kind of fit it so that when it's in its stowed position, it can still be there. So it'll be powered off the 36 volt power supply that's on that connector.
These digital signals or analog signals? Like, are they like pulses or?
There's both. There's analog, and then the digitals I'm just going to use like a level shifter.
If you use a balun, that'll do it for you, like a split.
The original are these giant boxes, and they're a pain to carry around. So I'm trying to shrinkify it.
So you want to go all out? Use 2 microcontrollers, 2 ADCs, 1 wired for plus, 1 wired for minus. Something.
Yeah, I'm thinking the voltage divider, then summing amp.
Inverting amplifier on the negative side.
Well, the problem is that the same signal can be both positive and negative.
You're creating more problems than what you started out with.
That's what I started out with. It's the negatives that are all my problem. But yeah, if it was like these signals only go positive and these ones only go negative, no problem. This darn thing has some that go both ways. It's like you scale it down and then you summing amp to add half the voltage, so that brings all the negatives into positive, and then you do the math in the microcontroller to convert it back.
Okay, there's one more thing you can do. If your signal is floating, so basically you got to run into a transformer or something. If it's floating, you connect -15 to ground, and then you got 0 to 30 signal now. And then you voltage divide it. Maybe you voltage divide it first, pass it through a transformer so it's a floating output, and then just do it that way.
Yeah, it's not floating. And I need 20-some transformers in that little area.
Yeah.
Yeah, it's like these are the amp connectors. So I want to make a little backpack. So I've got like wire wrap pins that stick out. So I'm figuring I could do that, have a circuit board, bring it out to headers on slightly wider, and then have like a daughter board on top with all the ESP32 and the ADCs.
Okay. One more thing is if you can find an opto isolator, like an analog opto isolator, that'll do the trick for you. So you got to reduce the signal to like 0 to 1 volt swing, and then or like plus or minus 1 volt swing, pass it through an opto isolator, and now you could do the trick I said before. So on the ADC side, you're going to have ground and V reference, and on the other side, you can have it hooked up to anything like plus or minus 15 or whatever.
Okay.
Op amp to the proper way to do it.
Yeah, that seems to be what everyone's steering to. I thought that would have been like a more common problem, that someone would just have an off the shelf. Like, we got all these 3.3 volt devices now with their ADCs. You think, scaling would be a common problem that someone would have a prepackaged chip for. Seems not.
Sounds like you're having fun.
Oh yeah, it's like a full-time job trying to figure this out. It's like I've got that part. I've got it where this is also I can like create the tester for the individual cards. I've got it where I can like give it signal and it thinks it's running the car. But there's like other outputs I need to be able to see without having. Right now I'm like I have a little pin in the block and I'm just one at a time putting my meter on. And it's a real pain.
God.
So. And then I got this whole contraption is the prototype tester for the safety signal generator. That's the next card I'm working on. So, and this simulates like the pedal signals.
Oh wow!
Yeah. So
Ian, there's one more option: differential ADCs. So a differential ADC, you just like it's most ADCs are like there's one input, one ground. Differential ADC has 2 inputs. The problem is both inputs have to be within 0 to VCC range. But
these the 115s I've got. They are capable of differential. I just need a heck of a lot more of them. I need 12 of them.
You can get analog muxes, which will let you switch between analog signals. ICs?
Yeah, I've got some of them around here. Somewhere. I kind of want to read them all at the same time. So, stuff that I'm thinking about. I got to go dig into those options.
Sounds like you got to quit your job and take on full time here.
Well, basically, I am full time in it right now. But I do. I'll be.
All right.
Fun.
Eric's had his hand up for quite a while. Go ahead, Eric.
Yeah, it's Ian. Actually, your camera shifted a little bit there, but I was just curious what I was seeing over. I don't know what if your camera's flipped or not, but over like there was some. I guess it's the wiring harnesses now that I saw, but that's like a mirror beside it, right?
No.
I just saw this.
Yeah.
This
It goes
rather.
this way. Yeah.
Yeah. I was just wondering
So-
what that was beside you there. It looked like something out of an H.R. Giger, like aliens painting or something. Whole bunch of weird pipes and stuff, but that's all just the wiring harnesses, right?
Yeah, that's the
coming
wiring
back.
harnesses.
Yeah.
All this monstrosity down there.
And then you got a mirror beside it, right? Because it's reflecting it. Yeah. Okay. All right.
Yeah. So that's. So I volunteer at a streetcar museum in Milton.
Right.
So this is out of one of the CLRV streetcars, so the ones they recently retired from Toronto on the streets. So that's the control system for it.
Yeah.
But
So
from
just
the-
I was looking at it in a kind of fuzzy picture in it. I couldn't tell what I was looking at, especially with the reflection. But okay, so that's all part of the same unit. Yeah.
Yeah, it's all the same unit. So this is out of one of the cars that ended up getting scrapped. So we just cut off a bunch of the harnesses.
Right.
So I've gone through and crimped the terminal on and terminal blocks. So I have everything kind of dangling there. Now I can pick out the signals I need, like that would go to the contactors under the car. So those will go here, and I'll simulate all the relays under the car and then send the feedback signals because it needs them to make all the safeties. And then like the manufacturer, they had made this simulator box. So that when you don't have the actual streetcar there, it'll provide like the feedback that the motors and their currents. So I have to fix like these first because the ones we have are broken. So I got to fix this and then fix the ECU and then I can fix the cards to keep the darn cars running. So
nice.
Yeah, there's 27 cards in that.
And you just have to. Next step would be running a simulator, like writing a simulator, right? So that you can then, on your computer, run the streetcars, right?
Oh yeah, that's why I want to because I need the monitor first to get the outputs.
Yep.
And then I could hook so this is the wire that simulator box connects to. So in theory, I could hook a microcontroller up to this and actually give it the pedal signals and drive it. And so once I have that, then I can test the cards I have to make sure they're good. And then the problematic ones I make up. Like this is the card number 3. I made a circuit board. You just plug the card in and it gives all the inputs and outputs so I can quickly check. I just wiggle this back and forth, and if the lights light up in the right way, I know that card's good, move along. Or if they don't, then I can grab the schematic and just start going through with my my scope to figure out which transistor the leg rusted off on.
I can see it now. Microsoft Streetcar Simulator 2026.
Yeah, that's the fun thing is like kind of when I get this done, in theory, I could hook it up to like a model train.
Yep.
You could actually use like a pedal controller and this to control a model train.
There you go. Somebody in this group must have a train set in their basement.
I've got one right there. It's in the closet too.
Yeah. Yeah. All right. Very good.
That's what's going on here.
Cool. I think we got one last person here. Wayne? You there, Wayne? Maybe you fell asleep.
Hello.
Oh, hi there. There you are.
Yeah, I have to mess with the microphone. Sorry. So I also experienced a flood like Al. I think it might be the same flood. So my basement is kind of down, or was down from until just maybe today. What that means is I don't have a bench and I don't have the ham shack. My antenna itself is basically kind of ripped out of the ground where I was passing the transmission line because they had to also remediate the outside wall. So I don't know when I'm going to have a working shack again. But they did declare success in repairing my basement. It's been 6 months since I've had no basement, and we just started moving some stuff down. I think it'll take us, I don't know, weeks to put it done. But that's where I am. So nothing on the bench.
Cool. All right. Let's see. I think that was everybody. So, does anybody else have any questions or comments or anything before we sign off?
Yeah, 4 days of May. Hotel space is going fast, so whoever wants to go, get going. Eric, you didn't register yet. That's it for me.
I have a comment relating to something that was an email in the SOAREX group about storing stuff, like storing components and whatnot. And I looked at the video there with where the guy has he takes little plastic bags and puts the components in the plastic bags and writes down all the stuff about everything and stores it away. And that'd just be a nightmare. I can't imagine trying to do that with tons and tons of components, like the ones I can see in Peter's shelf to the left. Well, I can't imagine doing that. I have components to worry about.
It's taking him weeks. It looks nice.
Oh my God.
There's so much info he puts on those tags.
I got 1, 2, 3, 4, 5, 6, 7. I've got 7 boxes here, plastic boxes, and I've got most of my resistors and capacitors in them, and most of the connectors, for example, for the spectrum analyzer and the scope. And but that's all I've got. I've got no surface mount stuff yet, fortunately, maybe. But I can just imagine it's just going to be a real problem.
The shack is bad enough, but we got all the spare parts for these cars. I have an entire building of stuff I have to sort through. So we're using a product called Sortly. So as I'm going through sorting, we're using these cardboard boxes, and then I print a label with the barcode and where I stored it, and I've got 100 like skid-sized totes I got to go through.
Oh,
inventory. Yeah, it fills an entire building, like floor to ceiling. It's gonna take me years.
Sounds like a Barnsworth.
Yeah, it is a Barnsworth. Barn 5 is filled.
Well, I mean, to Peter's point in his comments on the thread, if you're starting out, the binder thing might not be a bad idea, but pretty hard to convert once you got something on the scale of Peter's, like repository of mankind's components.
Like each bin, like each drawer has got set, like a lot, especially with the SMD components, which is probably 1.5, 2 bins. And each drawer has at least two pill boxes, which hold, I think about 5 different values of V in each of those. And because I ran out of space, I just put the other parts in below them and on their tape. So there's a multitude of values in each drawer. So you can easily start losing track of where things are and how many you've got to find them. And hence you got to sooner or later, you're going to have to go to a spreadsheet. So the sooner you do it, the better off you're going to be. But like I mentioned, now they're not cheap, but those SMD books, they're nice and small. You can kind of put them away on a shelf and there it is. If I ever have to move into a townhome or something or an apartment, holy cow, where am I going to put all this shit? So, these capacitor and resistor books are probably not a bad idea. Failing that, an envelope with the components in would work as well too, because you can get a nice small box. You don't have to get that big box, and you get hundreds of different values of components in SMD anyway.
That's how I do my resistors.
Yeah. So this is the way we went at the beginning. Yeah.
So where do you get these books, Peter?
Just Google them, Amazon or eBay.
SMD book. Okay, I'll do that.
Yeah, they sell blanks, but I don't think they're all that cheap. But It's an idea.
Mm-hmm.
You can also buy like a capacitor kit that comes like that. Might be $60 or something like that, or $70. I can't remember.
And then they have them for all the different sizes.
Yeah, well, I would go 1206. You know, let's face it. I mean, I can't convince half the people I talk to even solder 1206. They're not going to go to 805. And 805, you should be able to manage some 805s even with poor eyesight, poor lighting. But 1206 for sure is not really that difficult. It really isn't.
I should have brought my SMD challenge boards to the 4 days at my cottage. You know, that goes down to 0201s. So.
Funny you mention that. That's not a bad idea.
Those are handy for learning how to do it.
Yeah.
Here, I don't know how well this is going to come out on the tape, but speaking of 201s, what size are these ones? Oh, they don't talk about it. See how this turns out. Look at the size of those guys.
Can't even see them.
Oh my God.
Yeah.
They were given to me. Phil here locally gave them to me to say, here, do something with them. Yeah, right. Let's see. I'll put one of my. Oh my God, it's even smaller than I thought. Let's see what that looks like.
Don't sneeze.
Where is it? There.
Oh, there it is. Oh my God.
Yeah.
That's like a mosquito bite.
Oh shit! What bin did I take it out of?
Oh, you got to update the spreadsheet now.
Oh well, one down. Anyway, but you know what?
He's got to start over again.
I can't mill a board that would take that footprint. But you know what? I could go to JLC PCB because they're cheap and just say, you know, give me some bunch of 201s or whatever footprint size that is, and then just try. You know what? If I don't do it by hand, I could probably do it by hand. I wouldn't want to do a whole board like that, though. I probably would take the effort just for no other reason than to solder a bunch of these on a board, then go into our Saturday breakfast and say to Phil, "See, you can do it." But anyway. One thing that I think I might be doing sooner than later is switching to solder paste and a heat gun, maybe, or even an oven. I think that might be the next way to go, and just for the most part, forget about a solder iron and the regular solder, but just go to the solder paste, and that will make things a bit easier as well.
Who was it at Eric's place had the green and white solder paste in the syringe thing? Who was that?
Oh,
you know?
I don't remember.
I don't know. Anyway,
I got some here somewhere.
I don't know who that was. I can't remember that.
I took a picture of
Those are the boards
it.
I'm talking about, by the way.
Big one?
Those are the boards I'm talking about that I could have brought to the cottage just for a lark. See if we could do them. It's a little kit that has all of those on it. You start with a 1206 and go down. See if you can make it to the 201s. It's maddening.
Well, why don't you? How many of those you got?
Probably about 5 of them or so, something like that. So next time we have a gathering, I'll bring them along.
Okay.
Yeah.
Cool.
I got 2 of the solder paste. I haven't used it yet, though.
Oh, no. He's got to be hand soldered.
No, I get these hand soldering that. That's not a big deal. I think, though, but going forward for the ease of things, and I think solder paste is the way to go.
Yeah.
Mm-hmm.
Anyway.
Okay, I think we're done. If anybody else has anything to say. Okay. Well, have a good evening. Have a good evening, everybody. And good weekend, and take care.
Thanks for hosting it, Eric. Ken, good. Thanks.
Yeah. Cheers, everybody. Good.
Yeah.
Bye.
See you in February.